exist, because watch. Well, come back here, pencil. I want it blue, I said. There we go. F prime of x is 2/3 x to the negative 1/3, which is 2 over 3 times x to the 1/3. Since the numerator is a 2, there are no values of x that make this derivative 0. But there is an x in the denominator. F prime does not exist when that denominator is 0. And here it's when x is 0. But that's going to be a critical number. So we look at the sign of f prime about the critical number. Remember, f prime's got a cube root in it. Cube root of a negative number is negative. So when I put a -1 in there, I get a negative in the denominator and a positive in the numerator. But when I put a +1 in there, my derivative is going to be positive everywhere. So the graph is going to decrease and then increase. So it decreases to the left of 0, and it increases to the right of 0, which makes 0 a relative minimum. So that's the information from the first derivative. Now my second derivative. It's going to tell me about the concavity of this graph. I'm starting from here, and when I take the derivative, I take -1/3 times +2/3 and get -2/9. Take 1 away from -1/3 and I get a -4/3. So in simplified form, that's a -2 on top and a 9 x to the 4/3 on the bottom. A 4/3 power is a cube root, then raised to the 4th. Here, I again have no factors in the numerator, so my second derivative is never 0, but the second derivative does not exist where the denominator is 0, and that is at x is 0. When I look at the sign of the second derivative, f double prime, notice that, again, this is something that eventually is going to be raised to the 4th power. An even power on a negative number is going to make it positive. So my denominator is positive no matter where I am on the number line. Take any positive number divided into -2, and my second derivative is always negative, which tells me my graph is concave downward everywhere. It's not really concave downward at 0, so I've got to write that it's concave downward from -infinity to 0, and then again from 0 to infinity. It has no concavity at that point. Now we're going to graph this, so let's go back up here and plot f of 0. F of 0 is just -1. So our graph has to do all the stuff that we said above. Here's the ordered pair at 0, -1. Remember that there's no derivative there, so it's not going to have a horizontal tangent line. But the graph has to drop, hit that point, rise again, but always be concave down. So in order for that to happen, the graph is going to have to do some version of this. Come to a sharp point there. So notice that's decreasing and concave down. And now we've got to increase and be concave down. Those arrows don't turn around. They continue slowly concave downward, but we have that sharp corner where the derivative doesn't exist. See? Kind of cool. We needed to know the concavity to help us explain the sharp corner in addition to the no derivative being there. Now, one last thing I want to mention from the rest of this section is that we have a nice byproduct of the second derivative telling us about concavity, and it's going to be called the second derivative test for relative extrema. Now, the only potential location for a relative max or relative min is at a critical number. So let's start by saying let x equal c, be a critical number for f. Now, instead of looking at intervals around the critical number and the sign of the first derivative, we have an option. If we're going to calculate the second derivative to help us with concavity, it can also help us with determining whether we have a max or min. We're going to look at two cases. We're going to take our critical number and look at the sign of the second derivative at the critical number. If the second derivative is positive at the critical number, then I know that at that critical number, the graph is concave up. In order for the graph to be concave up, the critical number then has to be at the bottom of a concave upward portion. So if the second derivative at the critical number is positive, the graph is concave up, which tells us f of c is a relative min. If by chance I plug my critical number into the second derivative and get that it's negative, then I know my graph is concave down, and so f of c is a relative max. And I have this little picture to help remember it. I'm taking two derivatives and getting something positive, so here I draw two plus sign i's, and I know the graph is concave up, so it would be a minimum. If the second derivative is negative, I'm going to do two minus sign i's. The second derivative is negative, and it's sad, so it's concave down, and the relative max occurs. The only bad thing about this test, other than the fact that you'd probably have to compute a second derivative, is that if the second derivative at c is also 0, then this test fails. And you don't get any conclusion. So go back and use the first derivative test. We'll use this when we do optimization problems in section 4.6. So I'm going to work one example of showing you how you can use the second derivative test to determine relative max and mins. So let's let f of x be 8 times the square root of x minus x. And let's use the second derivative test to identify any relative max or min. So let's see, I'm going to take a derivative. Remember that the square root of x is x to the 1/2. So I bring the 1/2, multiply with the 8 and get a 4. Take 1 power away from 1/2 and I get a negative 1/2. Derivative of x is 1. So this is same as 4 divided by the square root of x minus 1. We're going to set f prime to 0. So I'm going to have this equation to solve for x. So let's move the 1 over. Let's multiply both sides by the square root of x. And now let's square both sides. So I get one critical number at x is equal to 16. Now let's skip the rest of the first derivative test and let's go straight to the second derivative. So I'm looking up here and I'm taking another derivative. Negative 1/2 times 4 is a negative 2. Take 1 away from negative 1/2 and I get a negative 3/2. So my second derivative looks like negative 2 over x to the 3/2. Now I'm going to take my critical number and I'm going to plug it in for x. (16 to the 3/2 means the square root of 16 cubed. So that's a positive number. Divide that into a negative 2, I'll get a negative number. So my second derivative is negative, tells me I have a relative max at x is 16. That's it. That's how you use the second derivative test for relative extrema.